Okay, so Unit 4, Gases and Atmospheric Chemistry. So this week we're talking about the rules of gases. And to start with, we're going to talk about properties. So before we talk about gases, let's go over and talk a little bit about the other states of matter. Solids, we define a solid as having a definite shape and volume. All right. In other words, you put it in a container and they just sit there. They don't do anything. They don't change their shape. They don't change a volume. They just kind of sit in their spot. They're incompressible virtually. You can't really squeeze them, and they definitely don't flow. And there's a little animation showing a chunk of solid in a beaker. You move it back and forth, and it slides across the bottom, and the particles are not able to flow past each other. All right? Again, empirical means with our senses what we observe, etc., etc. Empirical properties of liquids. They assume the shape of the container. You pour some liquid into a beaker, and that liquid flows to the bottom of the beaker, and it takes the shape of whatever is you've poured it in. It has a definite volume, which means you pour it into the beaker, and that amount in which it occupies, that space in which it occupies, is constant. All right? So you put 50 milliliters in the beaker, it's still 50 milliliters if you pour it into another container. It is virtually incompressible. If I were to take a syringe and put some water into it, I cannot readily squeeze that because the water takes up so much of the space and I can't squeeze it into a smaller space. So I cannot compress a liquid and it readily flows. And that's a comment on the particles where they're able to move past each other as you slosh that container around. And so you can pour it, it moves. If you move the container, it readily flows. Talking about gases, and I don't have an animation for this one, but a gas assumes the shape and volume of the container. So it doesn't matter how much of a gas you put into a space, that gas will automatically fill the entire space. All right? So if I were to take, even though there's even air in the room already, even though there's a gas in the room already, if I were to take this propane cylinder and I were to let some propane out, okay, I've let some propane out, that propane is not going to just sit here in front of us in the room. It's going to spread out, and it's going to ultimately fill the entire room. Even though there's already air particles there, there's so much space between those air particles that that propane is going to be able to fill into all corners of the room and kind of spread itself out evenly and take up that shape. Whatever the shape of the room is, it's easily it fills it easily, and it assumes the shape of the container. It doesn't matter what gas there is. They all kind of spread out so they're nice, evenly distributed. Highly compressible. I can easily compress a gas if I take the syringe. If I draw some air in, I got to find the open valve way. So if I draw some air in and I close it, I can easily compress a gas. All right? I can squeeze that down to a smaller volume. I can actually draw it out to a larger volume. The plunger will end up going back to where I started, the volume that I initially put in there. And so it's easily compressible, and it readily flows. Okay, so what we want to talk about is, what is it about gases that makes them have all of these interesting properties? And in order to make sense of that, we need to review the kinetic molecular theory. All matter is made up of particles, and they're in constant motion. If an object gains heat, its particles have more kinetic energy. That's why it's called the kinetic molecular theory. Remember, kinetic energy is the energy of motion. Anything that moves has kinetic energy, even gas particles, or particles in a solid or particles in a liquid. The hotter something is, the faster the particles move. That makes good sense. Energy is transferred from one part of an object to another by means of collisions. So if we have the heating of a metal spoon or even a scupula, I got a scupula in my pocket, And if I were to put that at one end of it in a Bunsen burner, the other end would eventually get hot, right? We call that conduction of heat. We now know that that's the particles in the metal starting to vibrate. They collide with adjacent particles. They vibrate, which collides with adjacent particles, etc., 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 and the heat is transferred along the line. Okay? Types of particle motion. So now we're probably going into more detail than you've probably ever learned in terms of kinetic and molecular theory. But scientists have sat down and thought very closely about how particles can move. There are essentially three types of motion that a substance, that any object can have. This is not true just for gas particles or solid particles or liquid particles or molecular particles. This is true for anything. Any object, if you think about it, can only have these three types of motion. Translational motion, straight line movement, that you move from one place to another. That's not a big deal. So if you've got a molecule and it's here and it moves to there, we say it's a translation. Straight line motion. That's not a big deal. Most of the motion we encounter is translational, right? You walk down the hall, you're translating down the hall, right? You're moving in a particular direction. Same within your car. You get in the car, go down the road, you're just going straight. Rotational. That's obvious. Any object can rotate as well. You want to avoid rotational motion in your car. That wouldn't be a pleasant experience. If you're going down the hall, I suppose you could do rotational motion. You'd look a little goofy. Maybe at a dance, you want to do rotational motion, right? No? Rotational motion? No? I don't know. It's rotational motion. Atoms can rotate. Molecules can obviously rotate. Vibrational motion. Now, vibrational motion does not necessarily take place in all objects. If you're talking about a simple atom, like just one atom, it really can't vibrate. It can rotate and it can translate, but it can't really vibrate. I guess it can vibrate like this. I guess it can vibrate in a solid. If it's in a solid, it can move back and forth. The reason I guess it moves back and forth if it's a single atom is because it's being encountered by other atoms. There's some kind of bond there. If you want a vibration to take place in a molecule, there has to be a bond of some sort. If we're talking about a solid, maybe like a bunch of iron atoms in a piece of steel, all right? All of these iron atoms are packed together, and they're actually feeling the presence of each other. They're actually being attracted to each other a little bit. So when they vibrate back and forth, then they're actually responding to the forces that are being applied by adjacent atoms. In a gas, a single atom can't vibrate. It can go off in straight line motion. It can be rotating, but it can't really vibrate because there's nothing to vibrate up against. If we have larger, more complex molecules, like carbon dioxide, all right? Carbon dioxide has bonds within them, which means this carbon dioxide can travel in a straight line, all right? It can rotate, all right? And it can also vibrate. Each of these atoms can vibrate with respect to each other. I think we all know that carbon dioxide is what we call a greenhouse gas. A greenhouse gas is a gas that's in our atmosphere that has the ability to catch heat coming from the earth and trap it and then re-radiate it back down to the ground. That's why our earth is warm and habitable. Because if we didn't have greenhouse gases in our atmosphere, all of the heat that came into the earth that would come from the sun, the ground would get hot, kind of like a piece of steel on a hot sunny day, right? You touch that steel, whoa, that's really hot. That's from the energy coming from the sun and heating it up. Then it re-radiates it as heat energy, and that heat energy tries to go back into space. If we didn't have an atmosphere, all of that heat energy would re-radiate back into space, and the air would be cold. The ground would be hot, but there would be no air if we didn't have any atmosphere. So then it would be like the surface of the planet would be hot, but this high off the ground would be unbearingly cold. We wouldn't survive. Greenhouse gases are important things. So what do greenhouse gases do? How do they trap the air? It has everything to do with this vibrational motion. If you put something like oxygen in the air, that's good stuff because we breathe it. We need oxygen in order to survive. But oxygen can't really vibrate. It can really vibrate in one way. It can have the oxygens come together and then spread apart. In other words, the oxygen atoms can do a little bit of that. That's about the most that an oxygen molecule, can do in terms of a vibration. But as soon as you add a third atom, you have all kinds of different vibrations. Many, many different ways of vibrating. Each one of those different vibrations is another way for the molecule to absorb heat. The more possible vibrations a molecule in the air can do, the more heat it catches, and the better it is at being a greenhouse gas. So depending on how they move, determines on how much energy they can absorb. Because remember, heat is the motion of particles. And the more ways in which a particle can move, the better it is at absorbing heat. That's what makes carbon dioxide such a good greenhouse gas. The problem is if we put all kinds of carbon dioxide into the atmosphere, we're going to catch more and more of the heat, and then the Earth is going to heat up, and then, well, you've all heard the stories. Let's keep going talking about our particles. So we now want to talk a little bit about the way order comes into play when it comes to the states of matter. This is a little introduction to a concept you'll learn next year called entropy, but it's not a big deal. We won't bother with it right now. Just we want to talk about the way particles exist in solids. They're highly ordered. In other words, they're sitting in nice little rows and crystals. They have very little translational motion. Vibrational motion is really what dominates in a solid. In a liquid, you've got a combination of a little bit of translational. They're able to move past each other, but they're not able to move free out of the liquid. So you got a glass of water. Those particles are moving around. They're moving around within the liquid. You put some ions in there, they're moving around as well. Which means it does undergo rotational, vibrational, and translational. And then gases, they're the most disordered. Okay, now let's talk a little bit about temperature. So now that we've talked about the way we can imagine gases, because that's really what it's all about, in our minds being able to think about what the particles are doing and how they're behaving. And now that I've described to you as gases as being absolute chaos, particles going everywhere, rotating, vibrating, translating, all kinds of motion. We're now ready to talk about some very important properties when it comes to gases. Scientists have determined that there are 4 numbers that anyone needs in order to define a substance, solid, liquid, or gas, but we're going to primarily concern ourselves with gases. The first one, we've already encountered it, and I didn't really talk much about it, and that's because it's not that exciting, and the first one is volume. You don't have to write this down. We'll be writing it all down later. But we need to know how much of a substance. It's volume, all right? And that's something that's fairly easily measurable. If it's a liquid, we put it in a graduated cylinder or maybe even a burette. If it's a solid, we can measure its dimensions or put it in some water and have it displace some water. We can measure the water. So volume is the number of milliliters, the space it occupies. The second thing is the temperature. What temperature is that substance at? Because a piece of ice that's at -4 is going to have actually quite different properties than a piece of ice that's at 0 and on the verge of melting. Okay, so temperature also is a very important defining factor of a substance, and that's why I'm going to talk about it here for a moment. I'm going to just keep going on this list. The third thing is pressure, all right? What kind of pressure is that substance under? Is it out in the vacuum of space? Or is it here on Earth just at kind of regular pressure? Or is it buried under the ground under huge pressures, right? And we hopefully have an idea that in different situations, things are going to behave differently, right? Materials do behave completely differently in the low pressure of outer space, or even just space at the space station, than they do here on Earth, right? So pressure, very important as well. And the last thing that defines any substance, but we're primarily worried about gases, is the amount of the stuff we have. I put an N there. That stands for number of moles, right? So how much stuff are we talking about? Are we talking about a lot of stuff or just a little bit of stuff? A temperature is a measure of the average kinetic energy of the particles in a substance. If something's hot, then there's a lot of kinetic energy in the particles. They're moving fast. If something's cool, then there's not much kinetic energy in the particles and they're moving slow. Here's my really exciting animation here. Ooh, did you see? When I clicked cool, they slowed down. Because it's a kinetic energy, it's not as simple as fast and slow. Heavy particles will automatically move slower, and lighter particles will automatically be moving faster. And that's because heavy particles carry more kinetic energy. It's also an average. It's not like the particles in a gas are on a highway. On a highway, everybody's kind of going the same speed. I guess you could have some fast and slow movers. But in a gas, the particles, and all substances, all types of matter, the particles have varying speeds. Some are going slow, some are going really fast, but most of them are in the middle. And so we've got this average, okay? So we've got slow movers and fast movers, and then we've got some that are in the middle. Okay, temperature is related to the speed. There's a little note about thermometers and how we measure things. We use a thermometer to measure temperature. Again, that's one of those things you've used over and over again. It's something that I really don't need to show you how to use. 0 degrees Celsius, freezing point of water, right? 100 degrees Celsius, boiling point of water. Now, other important temperatures, way down here, negative 273, absolute zero. And I'm going to talk about that just in a moment. It turns out that nothing can get colder than minus 273 degrees Celsius. The Kelvin scale has exactly the same size, degree units as the Celsius scale, except the only difference is that it starts down at the very bottom, or the coldest possible temperature. Because it made good sense to, if you had a coldest possible temperature, why not define that as zero, the starting point of temperature? And so 0 Kelvin is negative 273 degrees Celsius, which makes then our 0 degrees Celsius 273 degrees hotter than that, and therefore it's at 273 Kelvin. And the boiling point of water then is at 373 Kelvin. We're going to be using the Kelvin scale quite a bit. There's a very simple, easy way to convert. If you have the Celsius temperature, just add the 273 degrees and you'll turn it into the Kelvin temperature. How does the thermometer work? Okay, so remember, all the particles are bouncing around and moving around. And the air particles are bouncing off of this bulb. It's actually bouncing off of everything here. But this bulb contains a reservoir of some alcohol, all right? There's old mercury thermometers. You've seen them with the metal in there, the shiny metal. We don't use those anymore because if you break them, you got mercury in the air, and mercury's bad. So what happens? The particles strike this, and they strike the glass, and the glass particles start to vibrate. Then the glass particles vibrate up against the alcohol particles, which is a liquid. And what does that do? That kind of causes everything to kind of bounce up against each other and bubble up. And I'm trying to think of an example of what I'm talking about. You know, you're not going to be able to think of it. There used to be a Fisher-Price toy. It's got to be 1 million years old. That has the wheels and the popper in it. Pop up, pop up, pop up, pop up, pop up, pop up. You know what I'm talking about? And all the balls go, yeah, that type of thing, right? Okay. So you can imagine that's exactly what's happening in a thermometer. Right now, the heated air particles are bumping up against the alcohol particles. And so what are they doing? They're all bumping up against each other. Now gravity's trying to pull those particles back down into a nice little pile, just like in the popping machine. But because there's always these other particles bumping up against it, it causes those particles to bump, 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 and then it gets to a certain height. If it gets hotter, it means there's more bumping going on, and it bumps to the top. If you could get into your magic school bus and you could zoom in to the surface of that alcohol, even though it looks like a nice line here, it would be a chaotic there would be particles bouncing around and trying to get out and then falling back in, and it would be a chaotic surface, just like the inside of the popping machine. If you could build a big enough popping machine, the Fisher-Price popping machine is what I'm going to call it. Let's say you could build it with a big cylinder above it, and you put more balls in it. If you went slow, the balls would just kind of pop up a little bit. It'd be like cold. But if you ran fast with that machine going, right, you can imagine, pop, 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 it's popping like crazy, all those little balls would rise up to a higher spot. You could put a mark on there. And you could probably translate that into the speed of your running, right? It would be like your speed. But in this case, it's the kinetic energy of the particles that are around it. If we bring this outside where it's cool, there's less energy going to that. It settles down and goes to a lower temperature. That's the way a thermometer works, all right? There's some chaos going on in this little thermometer. Okay, so let's finish off by talking about a couple of little definitions here, just to complete this. I misspoke a little bit with the thermometer. We've talked about intermolecular forces. They're the forces that hold adjacent molecules together. They don't hold the molecules together. That's intra. But inter is what holds adjacent molecules together. Right now, in this alcohol that's in this thermometer, there are actually some hydrogen bonding going on, and that's what keeps this a liquid. Okay? A moment ago, when I was describing it to the way this thermometer works, I said gravity pulls the particles back down. It does in the popper. That's what keeps the particles from flying out of the popper, gravity. But in a liquid, and when we're dealing with the mass of little molecules, gravity is a very small effect. There's not a lot of gravity holding a molecule down. What keeps this in the liquid state is intermolecular forces. The hydrogen bonding that exists between the alcohol molecules, as the thing is trying to pop them up and push them up and expand them, they're being held back down by hydrogen bonding. An alcohol molecule tries to escape, and then it's being held back down by hydrogen bonding. Okay? So intermolecular forces is what keeps things condensed. If the intermolecular forces are weak and they're not strong enough, in other words, if the particles are not sticky enough to hold together, then they're able to fly away in all directions. And then we've got a gas. So when something has low intermolecular forces, they're able to get away from each other. They're able to fly apart from each other. And they exist then as a gas. If they've got high intermolecular forces, they'll be sticky to each other, and they will exist as a solid or a liquid. We can cause a solid or a liquid to vaporize and become a gas by giving the particles so much energy that they can't hold themselves together. They're bouncing off of each other so hard that, boom, they go off and become a gas, like when you boil water. When you boil water, you've put so much kinetic energy into the particles that they bounce off of each other and take off into the gas state, and away they go. All right? Okay. I'm not going to show that movie. Nope. There's the homework.